The world after the collapse does not kill you with violence first, it kills you with cold. Not the cinematic kind of cold, but the wet, creeping, bone-deep kind that strips heat from your core faster than you can replace it. When everything around you is soaked, your clothes, your pack, your tinder, the ground itself, the environment becomes a kill mechanism. Moisture accelerates heat loss, and heat loss accelerates cognitive failure. The moment your hands stop responding, fire is no longer a skill. It becomes a mathematical impossibility. That is the point where most people die. Not because they lacked fire-making knowledge, but because they misunderstood the physics of survival. You're not fighting the rain. You're fighting entropy. The collapse eliminates the luxury of redundancy. In the old world, fire was convenience. In the wet world, fire is the only remaining shield against calorie bankruptcy. The condition where your body spends more energy trying to stay alive than it can physically absorb. Every second spent cold is a second closer to catastrophic energy deficit. And once the deficit compounds, you don't get it back. That is the multiplier rule of hypothermia. The decline is always exponential, never linear. Most people think fire is a spark. They think the goal is ignition. Wrong. Ignition is irrelevant if the flame dies before it builds momentum. In a drenched world, survival depends on continuity, not ignition. You don't need a flame. You need a heat system, something that can cut through moisture, wind, and failure. That is why the 5 tools in this analysis matter. They are not classic fire starters. They are fire continuity devices, tools engineered or repurposed to generate, amplify, and sustain heat in an environment designed to extinguish it. Each one is chosen because it defeats a specific failure mode: water saturation, broken gear, cold hands, depleted calories, or lack of oxygen. Each one is part of a system, because in the post-collapse world, fire isn't a moment. It's an operational protocol. And without a system, you don't survive. Fire is not an element. It is a reaction. And nothing triggers that reaction under catastrophic conditions like a ferro rod. When everything is wet, swollen, and refusing to burn, the ferro rod becomes the only spark system that ignores the collapse entirely. It does not care about moisture, fuel type, altitude, or temperature. It produces molten metal at roughly 3,000 degrees Celsius, a temperature that overpowers the wet film on most materials before the environment has time to smother the reaction. That is why the ferro rod survives when matches dissolve, lighters drown, and friction fire becomes a fantasy. It is the last reliable ignition source when the world is soaked and hostile. People misjudge the ferro rod because they misunderstand what it actually does. It does not produce sparks. It throws burning particles. These particles are the ignition equivalent of a shotgun blast. Violent, numerous, and hot enough to carve micro scars into metal. That thermal violence is what makes ferro the apex hard condition tool. The physics is simple. The colder and wetter the world becomes, the more valuable high-temperature reaction spikes are. Lighters rely on vapor, not heat output. Matches rely on friction, not molten metal. Ferro rods rely only on physics, which is why they never fail, unless the user does. And the user fails often. The collapse exposes every confident mistake. People scrape the rod instead of shaving it. They push the striker outward, knocking their tinder away. They use the wrong angle, too steep and the sparks scatter. Too shallow and the rod glides without generating heat. They treat wet tinder like dry tinder, as if the environment hasn't changed the rules. They attack the rod aggressively instead of building an ignition bed. They expect fire when they haven't earned heat. The correction is a protocol, not a trick. The rod stays anchored. Your striker moves, never the rod. Pull the rod back while the striker remains locked. This prevents you from destroying your ignition nest. Build a shaving pile first. Thin curls of ferro scraped from the rod's surface. These micro shavings ignite explosively when hit with a proper strike, turning a weak spark into a heat pulse. Shape your tinder into a funnel so the molten metal concentrates rather than disperses. If the world is wet, manufacture tinder, cotton, dryer lint, jute, rope core, anything that absorbs molten heat rather than repelling it. Wet bark is not tinder. It is structural biomass. Treat it accordingly. In high wind, reduce exposure by building a spark corridor. One hand blocks the lateral gust, your torso blocks the frontal gust, and your tinder sits inside a depression or behind a piece of debris. Sparks don't fight the wind, they travel with it. Align your corridor so the wind delivers the sparks into the fuel rather than away from it. Moisture is defeated through heat and concentration, not effort. The ferro rod's true value is psychological and tactical. When all other systems fail, it remains. When hypothermia tremors sabotage fine motor skills, you can still drag metal against metal. When your gear breaks, the rod still throws sparks. When the world is saturated, the ferro rod is the one object that treats the apocalypse with indifference. It is the only spark that survives the end of everything. A spark is not enough when the world is drowning. In a storm-soaked collapse environment, moisture isn't a condition. It's an enemy with overwhelming numerical superiority. Every surface is saturated. Every piece of wood is swollen. Every breath of wind strips away heat faster than flame can build it. In this reality, the ferro rod gives you ignition, but ignition alone cannot overpower the environment's heat-killing momentum. You need something that doesn't negotiate with weather. You need a tool that creates a heat column, a vertical torrent of sustained thermal output that overwhelms moisture through brute force. That tool is the stormproof torch. The stormproof torch operates on a different physics model than conventional fire starters. Instead of relying on ambient oxygen and fragile surface combustion, it creates a self-feeding burn environment. Inside the torch, chemicals mixed with internal oxidizers generate a flame that does not depend on the external atmosphere. Wind cannot strip oxygen because the oxygen is already built into the reaction. Rain cannot cool the flame because the combustion temperature exceeds the thermal absorption rate of falling water. Wet debris cannot smother it because the flame isn't interacting with the surface. It's projecting heat into it like a cutting torch. This is why a stormproof torch ignites materials that laugh at sparks and shrug off lighters. It is not fire. It is applied thermal dominance. To understand its power, you have to understand the Venturi effect. The design of the torch channels air inward and upward, accelerating it as it rises. This pulls oxygen into the flame zone at high velocity, feeding combustion more aggressively than natural convection ever could. Paired with a chemical burn, this creates a flame that behaves more like a jet than a campfire. The result is a concentrated, directional heat column capable of drying wet wood faster than the environment can resaturate it. This reverses the moisture advantage. You're no longer begging wet materials to ignite, you're forcing them into compliance. But the collapse exposes misuse just as brutally as it exposes weakness. Most people waste torch fuel by treating it like a flamethrower. They hold it too far from the target, allowing heat to dissipate. They point it downward, causing the flame to choke itself. They torch surfaces instead of volumes. They fail to create a dry base layer, so their flame ignites the top of the fuel while the bottom remains soaked, causing the fire to collapse under its own weight. They use the torch as if they're impressing an audience, not fighting for survival. The correct protocol begins with constructing a platform. Wet earth kills heat. Elevate your ignition point using bark, scrap metal, a flat rock, anything that isolates your flame from ground moisture. Once elevated, use the torch not to ignite, but to dry. Think in terms of thermal phases. Phase 1. Remove surface water. Phase 2. Heat the internal moisture until steam vents. Phase 3. Apply direct flame only when the material reaches ignition temperature. You're not starting a fire. You're building a thermal runway. Angle the torch at 45 degrees so the heat rolls up and under the material, creating a convection pocket. This pocket traps hot air and accelerates drying. If the world is screaming with wind, position debris as wings to funnel gusts into the heat column, turning the storm into an accelerant rather than an obstacle. Wind is only a threat if you let it fight you. Redirect it, and it becomes a multiplier. A stormproof torch also carries strategic value beyond ignition. It can breach frozen materials, cut through synthetic debris, sterilize tools, and signal at distances greater than any match-based flame. In tactical collapse scenarios, heat is not just survival. It is communication, intimidation, and access. When everything is wet and broken, the stormproof torch is not your backup. It is your breakthrough device. The one tool that doesn't merely resist the storm, it weaponizes it. In a world where moisture infiltrates everything, your pack, your pockets, your shelter, even the air itself, almost every traditional fire method becomes a negotiation. But oil doesn't negotiate. Oil stores heat in a form that weather cannot dilute, extinguish, or corrupt. That is why the oil-based fire can, with a wick system, become something more than a fire starter. It becomes portable certainty in an environment engineered to erase certainty. When you carry oil, you are carrying chemical stability, caloric density, and the ability to generate controlled combustion even when the world is soaked to the bone. Oil is immune to the 3 collapse vulnerabilities of firemaking: saturation, oxygen volatility, and heat loss. Unlike natural tinder, oil does not absorb water. Unlike paper matches or butane lighters, it does not require delicate vapor pressure or friction. Unlike stormproof torches, it does not depend on single-use chemical spikes. Oil sits quietly inside a metal container, waiting, unchanged, regardless of temperature swings or storm exposure. The wick becomes the bridge between stored chemical energy and usable heat. A slow, stable thermal stream that endures long after sparks have failed. But the simplicity of oil is deceptive. Most people misuse it catastrophically. They stuff any cloth into the can, assuming it will wick properly. They overload the reservoir, creating unstable burn pressure. They select synthetic fabrics that melt or smother instead of absorbing oil. They build tall flames that waste heat instead of concentrating it. They use the fire can as a primary fuel source instead of a stable ignition system. A fire can is not a lantern, not a torch, and not a stove. It is a mobile heat reservoir engineered to deliver sustained thermal output that cuts through wet conditions with slow, disciplined efficiency. Understanding how to build one is understanding collapse thermodynamics. Your can needs mass. Thin aluminum warps under prolonged heat and collapses during burn cycles. Steel or heavy tin is ideal. Your wick must be natural fiber, cotton, denim, jute, or twisted rope. Synthetic fibers melt, shrink, or release toxic fumes. Twist the wick tightly, but not rigidly. Capillary action depends on microchannels. The wick should sit snug inside the can, but protrude just enough to ignite without dripping. Too high, and it flares uncontrollably. Too low, and the flame suffocates. The oil type defines the character of your burn. Lamp oil delivers clean stability. Diesel delivers slow, heavy heat. Used motor oil burns hot and dirty but becomes a viable collapse asset because it is everywhere. Even cooking oil, rancid or fresh, works because fire does not care about flavor. What matters is density and wicking performance. The thicker the oil, the slower the capillary ascent and the longer the burn. In a post-collapse survival logic, slow burn is life. Fast burn is waste. The real magic of the fire can is its ability to convert itself into a preparatory engine. Its flame isn't meant to ignite wood directly. It is meant to pre-dry it, to sizzle away embedded moisture, to act as a thermal anchor that stabilizes your ignition environment. Wet conditions don't require a burst of flame. They require time under heat. A ferro rod gives sparks. A torch gives bursts. The fire can give duration, which is the only property that defeats water saturation. Operationally, you begin by lighting the wick in a controlled posture. Shield the flame with your body and debris, not because it is fragile, but because stability matters more than intensity. Once your flame stands, feed it small wet sticks, not to burn them, but to dry them. Hold them above the flame like a kiln lid. Rotate them. Let the heat work slowly. After you've built a supply of semi-dry fuel, construct your ignition stack. The can becomes the heart of the system, radiating consistent heat while you assemble the rest. In prolonged wet collapse scenarios, the fire can become not just an ignition device, but a survival multiplier. It can simmer water, warm hands too numb for fine tasks, dry clothing, sterilize blades, create smoke signals, and provide night-long heating without constant tending. It is the closest thing to owning fire as an asset rather than chasing fire as a miracle. When everything else breaks, rots, or drowns, oil remains what it has always been, stored heat waiting for command. When the collapse strips away dexterity, when your hands shake from cold, when your muscles fire out of rhythm because your core temperature is dropping, the world stops caring about skill. It only cares about what still works. Chemical ignition tablets work. They don't require friction, pressure, precision, or even stable grip. They don't demand that you strike a perfect angle or maintain a steady spark corridor. They only require contact with flame or heat. Any heat. Sometimes even a focused ember. This is why, in the wet world, chemical tablets become more than fire starters. They become the last ignition system that still obeys you when your body no longer can. The science behind these tablets is brutally simple. Hexamine compresses chemical energy into a dense block that vaporizes into a flammable gas the moment heat touches it. Trioxane does the same but faster, with a cleaner burn. Magnesium composites ignite at lower thresholds than solid magnesium shavings but burn at similar temperatures. All three share one property that the post-collapse environment cannot negate. They produce their own momentum. They don't merely catch fire, they become fire. Moisture doesn't smother them because their combustion temperature overwhelms surface water. Wind doesn't strip heat because they output more thermal energy per gram than any natural tinder. Cold doesn't affect them because they don't rely on vapor pressure or fine motor ignition techniques. They are chemically inevitable. But inevitability does not mean efficiency. Many who carry tablets sabotage their own survival. They use them as primary fuel, burning tablets when wood could carry the flame. They leave tablets unprotected inside backpacks, allowing humidity to seep in and degrade burn performance. They place tablets directly on wet soil, letting the ground steal heat faster than the tablet can give it. They try to ignite them with lighters that fail in wind or ferro rods used improperly. Every mistake compounds, wasting the one tool designed specifically for conditions where every other method collapses. The correct operational protocol begins with elevation. Tablets must never sit on wet ground. A flat piece of bark, metal, bone, or ceramic isolates the heat. This isolation is not optional. It is the difference between ignition and evaporation. Once elevated, the tablet becomes a heat nucleus, not the flame itself. Your goal is to use it to generate a sustained thermal envelope around your fuel. Break the tablet into fragments rather than burning a full block. The increased surface area produces hotter initial flame and allows you to deploy multiple ignition points without sacrificing supply. Heat distribution is survival. Never put all of your thermal assets into one place. When using a ferro rod, don't attempt to light the tablet directly with sparks. Instead, heat a micro-tinder bundle first. Cotton, jute, bark fiber, rope core, and place the glowing bundle under or beside the tablet. Chemical tablets ignite aggressively once heat accumulates, and the molten reaction will cascade outward, amplifying the tinder's flame. If you are shaking from cold, do the opposite. Strike directly into a corner of the tablet. Chemical blocks flare from concentrated heat faster than diffuse sparks, so aim for the edge, not the center. Wind becomes an asset when you understand tablet behavior. Tablets burn hotter when fresh oxygen feeds the edges. Instead of shielding the flame completely, use natural barriers to channel wind toward the tablet while blocking it from carrying the flame away. A partial wind tunnel effect forces oxygen directly into the reaction, increasing combustion temperature and reducing ignition time for wet fuel. Chemical tablets also serve as a strategic redundancy. In the collapse, your hands will fail before your logic does. Fine motor skills deteriorate early in hypothermia, long before cognitive collapse. Tablets bypass that vulnerability completely. Even if your fingers barely close, you can still press a tablet into place. Even if you cannot coordinate a perfect ferro strike, you can still generate enough heat to initiate a reaction. Even if the rain crushes every spark you produce, the tablet will convert the tiniest ember into a self-sustaining flame. A tablet is not a luxury. It is a guarantee. And in the wet world, guarantees are almost extinct. When the world is soaked past reason, when every branch drips, every log bleeds water, and every breath feels heavier than the last, the problem is no longer starting a fire. The problem is overcoming physics itself. Wet wood does not burn because moisture steals heat faster than combustion can generate it. Every drop embedded inside fibers becomes a micro-heat sink, wicking away thermal energy and lowering flame temperature below ignition threshold. You cannot spark your way through that. You cannot torch your way through that. You cannot wish your way through that. The only method that breaks this physics bottleneck is to create a structure, an engineered thermal trap, capable of holding heat long enough to overpower moisture. That structure is the primitive fire accelerator, the micro-kiln. A micro-kiln is not a campfire. It is a combustion engine built from collapsed debris, stone, brick shards, scrap metal, concrete pieces. Anything heat-resistant becomes a building block. The purpose of the structure is simple: trap heat, reflect heat, and recycle heat. In a soaked world, fire dies because heat escapes faster than it accumulates. The micro-kiln reverses the equation by creating a chamber where heat cannot flee. Instead of losing thermal energy to the rain, wind, and wet ground, you create an artificial heat pocket where moisture is forced out of the fuel, not into it. This is where people fail. After the collapse, even skilled outdoorsmen fall back on campfire instinct: a pile of sticks, a spark, maybe some kindling. That method works in a forest brochure, not in a drowned reality. They build low, wide fires that disperse heat. They don't vent airflow properly. They place wet logs directly over weak flames. They ignore the moisture purging threshold, the point where trapped water inside wood turns to steam, ruptures fibers, and finally allows ignition. They expect combustion without structure. Collapse punishes that expectation. The micro-kiln begins with elevation. Wet earth is the ultimate heat thief. Build your base using rocks or scrap metal to raise the chamber off the ground. This prevents your ignition core from bleeding heat into soil. Next comes the walling. Three-sided enclosures create directional heat. Four-sided enclosures create total heat recycling. The walls must lean inward, funneling rising heat back toward the center. Leave a single intake slit low on one side, the venturi port. This port pulls fresh oxygen in as heat rises, creating a negative pressure pocket that accelerates internal airflow. This is what transforms a weak flame into an engine. Inside the chamber, the initial burn starts small. Tinder, tablets, ferro-ignited kindling, anything hot enough to carve out the first thermal zone. Once flame exists, the structure does the rest. Heat accumulates in cycles, even wet sticks, placed at an angle across the vent, begin to hiss as internal moisture boils. The micro-kiln doesn't care that they're soaked. It forces them to surrender moisture through steam purge. Once the purge begins, temperature climbs rapidly because water, your enemy, has left the wood. Now, combustion becomes possible. Not before. But technique defines outcome. You cannot pile wood too tightly. Smothering kills the airflow gradient. You cannot leave walls too open. Heat loss kills the moisture purge. You cannot use smooth metal for all walls. It reflects heat but doesn't store it. Optimal walls mix thermal mass, stone, brick, and reflectivity, metal. One holds heat, one bounces it. Combined, they form a thermal echo chamber. As the fire matures, you transition the chamber from ignition mode to sustain mode. In ignition mode, the goal is moisture expulsion. In sustain mode, the goal is fuel layering. Place semi-dry wood on the upper rim of the kiln. It dries from radiated heat before joining the combustion core. This creates a continuous pipeline: wet, drying, semi-dry, burning. A normal fire consumes fuel. A micro-kiln prepares fuel. That is the difference between fighting the environment and overpowering it. The strategic implications are enormous. A micro-kiln, once established, becomes a heat factory. It burns wet wood like dry wood. It stays lit through storms because the chamber shields the flame. It produces concentrated warmth capable of preventing hypothermia even when wind speeds tear through forests. It allows cooking, boiling, sterilizing, and tool forging in conditions that would normally extinguish every flame you could create. It is not a campfire. It is a survival infrastructure. In the wet world, fire is not a moment. It is a system. And no system defeats moisture more decisively than a well-built micro-kiln. It turns soaked fuel into obedient fuel. It converts hostile weather into irrelevance. It is the final stage of fire continuity, where heat stops being fragile and becomes sovereign. When everything is wet, the micro-kiln does not give you fire. It gives you domination over the one enemy that never sleeps: cold. The wet world kills slowly, then all at once, not through violence, but through the quiet erosion of heat, the steady siphoning of calories, the numbing of hands, the blurring of judgment. Fire is not comfort in that world. It is not ritual. It is not the romantic centerpiece of survival myths. In a post-collapse environment drenched in water and failure, fire becomes the only reliable barrier between you and a downward spiral of thermodynamic decay. It is the last system that stands between you and entropy. That is why every tool in this analysis mattered. Not because they create flame, but because they create continuity, the only property that matters when everything is wet and broken. The ferro rod is the spark that cannot be drowned. The stormproof torch is the heat column that ignores weather. The oil fire can is the reservoir that gives you time. The chemical tablet is the ignition that obeys even when your body fails. And the micro-kiln is the structure that turns wet wood into fuel instead of dead weight. Each tool replaces luck with physics. Each tool turns chaos into protocol. The collapse strips away illusions. It erases try, hope, maybe, and almost. In the soaked world, you don't get second chances and you don't get time to correct mistakes. Fire isn't a task. It's an operational system. Build it correctly and you survive. Break that system and the environment finishes the job swiftly and without drama. The truth is simple and merciless. In the rain-soaked aftermath of civilization, you don't rise to the occasion. You fall to the level of the systems you built. Fire is that system. And without it, nothing else you do matters.